All right, well, hi everybody. Thank you for coming. Uh, I'm Raphael, and this is my presentation in Lie groups and algebroids in Lagrangian reduction. It's kind of the shorthand name for it, but essentially, the entire point of my project is working on being able to simplify the equations that are required to describe the evolution of a mechanical system. So, knowing how a system moves in time. I'll start with a fundamental property of the universe. So the Lagrangian, that little L right there, is defined as the kinetic energy minus the potential energy. Action is defined as the integral of the Lagrangian with respect to time. And one principle of the universe that tells us what path a particle or a system is going to take is Hamilton's principle, which states that this action will be minimized over any interval in time. And this gives rise to the Euler-Lagrange equations, which are boxed here. And that's a set of differential equations that can help us determine the trajectory of a mechanical system. The Boltzmann-Hamel equations give the dynamics for something called an arbitrary basis for velocity. And so the usage of this is when we have constraints in a system, we might want to use a different system of coordinates. And one way of doing this is by using something called quasi-velocities, which are linear combinations of true velocities that don't necessarily correspond to the rate of change of an actual coordinate. And when we have these quasi-velocities, when we're using these, we get an extra term that pops up in our Euler-Lagrange equations, the term with the gamma right there, and those gammas are called the Hamel coefficients, which we can explicitly state or define in terms of a transformation from one set of known coordinates to our new, more useful set of coordinates. But sometimes this is not enough, and getting a more general understanding of where these coefficients come from is something of both mathematical and practical interest. Geometric mechanics is a field of applied mathematics that uses tools from modern geometry to help make some problems in dynamical systems easier. So the way that it does this is by representing the space of possible configurations of a system as a generalized type of space called a manifold. So that's my sphere here. That could be, that could be the point of a person on the Earth or something like that. And to every single point on this manifold, we can assign a set of tangent vectors. So vectors that are tangent to that point. And that set of vectors forms a vector space, which we call the tangent space. And this tangent space is where our velocities live. If you glue all these tangent spaces together, you get something called a tangent bundle. And the Lagrangian is a function of the tangent bundle because it takes a velocity and a position or sets of those coordinates and assigns to it a real number. So when we add over that, when we sum over that, then we're going to have that minimized. Some extra terms that might be worth defining are tau, Tm to m. That's a projection of an element of the tangent bundle onto its element in the manifold. So that'll take my tangent space and tell me what coordinate it corresponds to. And then there's some other coordinate transformations. So for example, the tangent bundle itself forms a space, a manifold. So you can take the tangent bundle of that, and then you have some other projections that might be useful. So we define dynamics as vector fields on the phase space, which is parametrized by position and momentum. So if you know the position and momentum of a system, then you can pretty much determine everything else you want to know. Or if you know the Lagrangian, then you can know what the state of that system is going to be later in time. And so if we have vector fields on the phase space, I can have a point that's momentum and position, and then I have a vector that points me in the direction where the system's going to go. And then I go to the next point, and that points me into a new direction, et cetera, et cetera. And so the way that we do this is, well, we have our Lagrangian. It's a function of the tangent bundle. And then a small variation in this Lagrangian is a function of the tangent bundle that brings us to something called the cotangent bundle of the tangent bundle. So for those in linear algebra, uh, the cotangent bundle is the set of cotangent spaces, and the cotangent spaces are the spaces that are dual to the tangent spaces because every vector space has its own dual space. Um, the dynamics is essentially defined as those vector fields that we're solving for, right? That's the big point of interest. That's the item that we're trying to find. And so it takes an element of the tangent bundle, so like a velocity and position. It takes a small variation in the Lagrangian, a small variation in the state of the system, and then it maps it to tell us the dynamics. And that's the main thing that we're trying to find here. Um, we can use something called a Lie group to reduce the motion, so we can exploit the symmetries of a mechanical system. A Lie group is a set of, it's a mathematical group that is also representable as a manifold, or rather that forms a manifold. And examples of this could be the set of possible three-dimensional rotations, or the set of rigid body transformations. For example, if I'm standing right here and then I move to this point right here, I've translated, I've rotated, but I'm still the same person, right? So that's intuitively what a Lie group is. We can use that to exploit the symmetries. So at the top we have the diagram that I had in the last slide when we have this Lie group. The tangent bundle of the Lie group is what we say isomorphic, or it can be transformed smoothly into a product between the Lie group itself and then the Lie algebra being something that can sort of generalize our notion of what velocities are and all of that. And when we reduce our mechanics, we can ignore the group part of our Lagrangian, of our tangent bundle. And so we get a reduced Lagrangian, which is just a function of the Lie algebra itself and brings it to the real numbers. And so schematically, you can see the diagram sort of simplifies. So what I did is I derived the Hamel coefficients that I was talking about earlier that show up in the Boltzmann-Hamel equations for the group of four-dimensional rotations, that's SO4, and then SU2, which parametrizes three-dimensional rotations, among other things, in quantum mechanics, without referring to any specific set of coordinates. Now, this can be useful for getting a more general idea of where the Hamel coefficients come from, and I don't need to choose what set of coordinates that I have to use so that I can obtain these coefficients, right? I don't need to have those transformation matrices that appear in the initial explicit definition. So for SO4, I found that, interestingly, the four-dimensional rotation decomposes into two individual three-dimensional rotations as far as the Hamel coefficients are concerned. And the way that this does it is a rotation in four dimensions is parameterized by six coordinates, and a rotation in three dimensions is parameterized by three coordinates. And there is sort of like a smooth transformation between the Lie algebra corresponding to four-dimensional rotations to the direct sum of two individual Lie algebras for three-dimensional rotations. And for SU2, I found that the Hamel coefficients are the same as what you would get for three-dimensional rotations, or the usual representation in classical mechanics, up to a scaling constant. I showed that the Heisenberg group can be applied in the Lagrangian framework, chosen as a configuration space. So the Heisenberg group in three dimensions is the group of matrices of this form right here. It has ones on the diagonals, it has zero on the bottom left, and it could be anything on the top right. And so last year, a group of researchers found the usage of the Heisenberg group as a configuration space in another formulation of mechanics called Hamiltonian mechanics. So it applies to constrained systems and can help us reduce the motion. I did this and applied it to the Lagrangian framework. And one way you could sort of schematically visualize how this reduces the motion is on the bottom right, we have a diagram right there that gives us a space of possible, a surface of possible places where a particle in some sort of modified problem, Kepler problem, can be. So I kind of modified it to fit the purposes of the problem of the Heisenberg group itself. But we can derive that sort of surface instead of having to look at all of space. And then the computer, when it makes the trajectories on the bottom left, it doesn't have to think as much and think, oh, well, it could be anywhere in space. Rather, it can lie anywhere on the surface. So before I move on to the next section, I want to mention a little bit what a Lie algebroid is. So a Lie algebra, I said, was sort of generalizing the notion of velocity. A Lie algebroid generalizes the tangent bundle itself. So it's an even further generalization that we can make. And one way to sort of explain the difference between a Lie algebra and a Lie algebroid is the identity element, or basically the number one in a Lie algebra, is going to take an element of the manifold or a point, and it's going to bring you back to that exact same point. Whereas the identity on a Lie algebroid might shift that point a little bit. So it might be a little bit confusing how that actually relates to mechanics, but over the last 20 or so years, it's been found that Lie algebroids allow for a more natural frame for mechanics. And so what I did with this is I showed how something called a connection on the Lie algebroid fits into the Boltzmann-Hamel framework. And the way that you do this, right? So a connection on a Lie algebroid, or a connection in general in mathematics, is something that can split your tangent bundle into two separate distinct pieces, or two separate sections. And so when you have those two sections, you can choose your connection to be, oh, well, one side of this space is going to be the side that's allowed by my constraints, and the other side is not allowed by my constraints. So that's roughly what a connection does. And I was able to relate this concept of the connection to Lagrangian mechanics, which is everything that relies on those Euler-Lagrange equations, through the Boltzmann-Hamel framework. And this gives us a more general idea of how we can approach constrained mechanics. And so Lagrangian reduction, which is this entire idea of reducing the complexity of the equations that are required to describe the motion of a mechanical system, that has plenty of applications in dynamical and control systems. For example, if I want to control a satellite here, there are so many different moving parts. If I want to get my satellite from Earth to Mars, well, there's gravitational influences, and there's parts within the satellite that I need to control to get to move efficiently. And all of these things we can work to derive some sorts of Lagrangians for, and ultimately we can reduce the amount of time that a computer has to spend on actually computing trajectories and all of this, or computing control inputs by using this sort of work to derive the equations and get simplified equations. So what I learned from this project, and some advice I have for future students, is to seek help from mentors. It was very important to seek help from mentors, because that way I know that I'm not a crazy person writing random symbols on a board. Don't let scary sounding concepts impede your intellectual curiosity. Algebroid was initially very, very scared to me. It's okay. And then if you're doing math, consider the practical applications, because people will ask that a lot. And finally, have fun with your project, because you can learn so much from doing this type of stuff in honors independent research. And some acknowledgements. I wanted to thank first and foremost Dr. Sarah Post for helping me so much with this project and helping me understand some of the concepts with which I was working, and also helping me validate my own work. Thank you to Dr. Chan for being my honors independent teacher and supporting me throughout this process. And thank you to Mrs. Kobayashi for her continued support as well.